Welcome everybody. In this video we are going to solve a problems regarding coordination chemistry. So in the coordination chemistry, basically the question says correct increasing order of wavelength in visible region for cobalt plus 3 complexes. Okay, so they have given 3 complexes. We have to predict the wavelength in the visible region. So we know that wavelength is inversely proportional to delta O. What is delta O here? Crystal field stabilization energy. So always we know that wavelength is inversely proportional to energy. Here energy is in the form of crystal field stabilization energy. So from this we can evaluate the above answer. So all are in +3 oxidation state. Only the difference is the ligands are different here. According to the spectrochemical series, strength of the ligand varies in the range, that is ethylene diamine. En is nothing but ethylene diamine greater than ammonia, and finally water. So water will be the weak ligand among the following. But here we know that wavelength is inversely proportional to energy. So the order would be reverse, that is H2O greater than NH3 and finally ethylene diamine. So order would be like CO, H2O taken 6 plus 3 and followed by ammonia in +3 oxidation state, and finally we have ethylene diamine 1. So this is the solution for it. Yeah, read the next question, that is pick out the correct statements with respect to manganese and this complex. We know the cyanide is a strong field ligand. So strong ligand, I can say strong ligand forms low spin complexes. They form low spin complexes and vice versa. If the ligand is weak, then it forms the high spin complex. So we know that manganese in free state, it is 4H2 3D5. Okay, so here in this, let's find out the oxidation state here. Let us consider manganese as X plus 6 into cyanide is a negative ligand -1 is equal to -3. So oxidation state X would be equal to +3. So in +3 oxidation state, here loss of 3 electrons results in the formation of a D4 complex. Okay, this is the D4 ion we have. So let us see the electronic distribution here. 1, 2, 3, 4, 5 d orbitals we have. 5 d orbitals we will distribute 1, 2, 3, 4. As I have said, it is a strong field ligand. Pairing occurs here itself, right? So next we have s orbital followed by the p orbital. So here we have d2sp3. So d2sp3 hybridization, and the complex would be with 6 ligands it forms octahedral complex. With 6 ligands it forms octahedral. Trick is, if 6 ligands are there, we can say that octahedral. If 4 ligands are there, we have to choose whether it is tetrahedral or square planar depending upon the ligand. If the ligand is strong field, then it forms, if the ligand is strong, it forms square planar complexes. If the ligand is weak, it forms tetrahedral complexes. Let's move on to the next problem. So here they have given which of the following has longest CO bond length. So they are asking about the longest CO bond length. So that longest CO bond length is directly proportional to length of C bond O is directly proportional to back bonding. Say for example, if back bonding increases, length of the carbon to oxygen bond increases. Okay, and length of carbon to metal decreases due to the formation of double bond. So I will write the structure. Say for example, consider any metal M. If it is bonded to CO, C bond O, so remaining ligands I am writing as such. So when back bonding, consider back bonding, when back bonding increases, metal and carbon will have double bond character. Okay, so and C bond O is triple bond, right? So that triple bond is now changing into double bond. So if bond order is decreasing, then bond length increases. So this is the thing, bond order is decreasing, bond length increases. So here back bonding increases when negative charge on metal increases. When negative charge on the metal increases. Here in the options we have seen that negative charge is more on option 2. In the first option 1 minus, in the second option 2 minus, in the third option it is plus, and in the fourth option it is neutral. So increase in the negative charge increases the back bonding. If back bonding is increasing, and CO bond length will also be obviously increasing, right? So the option would be B. So this was a very easy question in the year 2016. So that is NEET 2016, this question came. So the question states that which of the following pairs of d orbitals will have electron density along the axis. So along the axis we have dz square and dx square y square along the axis. So ligands, say for example if I consider octahedral complex, any metal octahedral complex, so ligands approaches towards the axis will repel better. So the ligands which approaches in between the orbitals will experience less repulsions. Okay, so the more electron density or the electron density is present on dz square and as well as the dx square y square depending upon the d1 complex. So see the next question. So they have given the correct increasing order of trans effect. So they have given some ligands, that is ammonia ligand, cyanide ligand, bromine ligand, C6H5 ligand, that is phenyl ligand. So it is a very direct question from your NCERT. So the correct order would be basically here the strong field ligand would be like C6H5 minus, followed by cyanide, followed by bromine, that is bromide ion, and finally ammonia. This is the series. So what is trans effect? Basically it is a very simple one. I shall consider the square planar complex. You can also consider octahedral complex. So any square planar complex I am considering, say for example I am taking ammonia here and chlorine here, and here I am taking cyanide as the ligand. So the trans effect states that the mobility or the leaving group capacity increases when the trans group is much effective. Here we have chlorine which is trans to ammonia, and here chlorine which is trans to cyanide. Here the trans effect of the cyanide is greater, that's why chlorine leaves fast than the ligand which is present trans to the chlorine. Okay, this is the trans effect. It was a very simple and directly from the NCERT. See the next question. John-Teller effect is not observed in. So basically what is John-Teller distortion? So it is the unsymmetrical filling of T2G or EG orbitals, or say for example if I consider the d orbitals, there would be 5 d orbitals. So when ligand approaches, this is a free metal ion, when ligand approaches near the metal ion, that free ion is broken down into 2 sets. Okay, broken down into 2 sets. One is with 3 orbitals and another with 2 orbitals. So this is called as what? Crystal field splitting. This would be T2G, which is called as triply degenerate, and this is EG, which is called as doubly degenerate. If you do not know, please know it. This is triply degenerate and it is doubly degenerate. So they are asking John-Teller effect. So what is basically John-Teller effect? Unsymmetrical filling of electrons of both T2G as well as EG. If T2G is unsymmetrically filled, then it is called as what? Dynamic John-Teller distortion. What is that? Dynamic John-Teller distortion. If T2G is unsymmetrically filled, it is dynamic John-Teller distortion. And if it is symmetry, I mean like if unsymmetry is in EG orbital, then it is called as what? Static John-Teller distortion. Static John-Teller distortion. Okay. So see in the options, so we have to make the filling of electrons, that is distribution of electrons. Consider D8. Let's consider D8. So they have given high spin, that means we don't have to consider pairing. Okay, so D8, I start filling it. 1 2 3 4 5 6 7 8. So in the both the cases they are symmetrically filled. Here these 2 orbitals are filled with 2 electrons each, and here it is also symmetrically filled. Both are symmetrically filled. Then there is no John-Teller distortion. So the correct option would be what? D8. So you can check all the remaining cases. D7 means less by 1 electron. So TTG will be unsymmetrically filled. Then it is called as dynamic Jahn-Teller distortion. So till now they haven't asked about the static or dynamic one. You can just remember as Jahn-Teller distortion, right? So I hope this answer is very clear to you.